My name is Joris Thibaut, and I'm the coordinator of e-CODUCT, which is one of the 3 projects which is running within a call on electrified reactors, implementing electrified technology. We have teamed up to organize a workshop on electrification and electrified technologies. And we did not limit ourselves to the 3 sister projects within that specific call, because in our network, we were aware of other projects within other calls that were in fact also making use of electrified technologies. So because of that, we teamed up in total with 5 projects, and that resulted also, well, not only in a major attendance of people belonging to the various projects, but we were quite happy with the number of people that has registered to attend this workshop on electrified technologies. We decided to call it the Electric Decade. We had a bit of a discussion like, well, how should we call it? We were talking also about the electric era. Well, we decided to stick to a decade because maybe even if a lot is already happening, it's maybe too soon to call it that we have entered the era of electrified technology. But well, we see ourselves as being in the decade towards that era. And a crucial aspect of that decade will be scale up, bringing electrified technologies from the laboratory to the industry. And I think that's why we got together the program which we have right now and which is on the screen right now, which has contributions from academic members, from industry, from research institutes. So I think we span the entire chain of technology development. And within this agenda, before we give the word to each of the coordinators or the representatives of the 5 projects, we will have 2 more overarching contributions. First by Franz Hürzenberger from ArcelorMittal on how electrification can help meeting the circularity goals, followed by Walter Vermeeren from Total Corporate R&D on electrification technology. So as you can see further, then we'll follow the 3 project presentations of the 2 sister projects within the call on electrified reactors, followed by a short break. And after that, we will continue with the 2 other projects, Titan and Storming. End to end, we will then have a panel roundtable discussion and also a question and answer moment where everybody from every participant can intervene via the question and answer button, the Q&A button, which you find just on the top of your screen, just next to the chat and in between the people list of attending. So depending on your language settings, you may see Q&R or Q&A, or maybe, well, I don't know what question and answer will be in your language, but that's what the button is referred to. Other aspects will be that presentations will be shared after the workshop, and also that the session is recorded for later consultation. And I think with those practical details, I think we're ready to move the word onwards to our first invited speaker, which is Franz. So Franz, the floor is yours.
Good morning to everybody. Can you hear me? Is it okay?
Yeah, we hear you fine.
Okay. Somebody is moving the slides, so I have good. For my person now, I'm next to employee of ArcelorMittal. I'm a so-called vice chair on energy and CO2 in Aspire, so the association for research of the process industry in in processes for Planet Partnership. And I'm also co-chair of set plan implementation working group number 6, so the so-called industry grouping in the set plan. And in the scope of these activities, we got the chance to do the study which is presented now here for you. So the study was already shared about half a year ago through the set plan implementation working group number 6 with the public. So after this exchange, I think you will also share the presentation with everybody. So I will only take out some slides now from this presentation to give you some idea about the situation of process industry towards electrification of the future. So in the next slide, can you go to the next slide? So there is just an overview of the overall energy situation in Europe. So total energy use, 60,000 petajoule a year. This is everything which is used as energy. There are losses, around 25% losses, and then around 75% of the energy is used in the different areas, and around 1/3 of the 75% goes to industry. So this is the general situation at the moment. Can we go to the next slide? So this is the situation for let's say the industrial sector, which are covered within Aspire. So around 80% of the total energy consumption in industry is covered by the Aspire sectors. And another interesting number here is that around take 25% of energy used in industry is electricity today. The rest is fossil energy. Can we go on to the next slide? So and then, so stop here for a moment. We got the opportunity to use the address methodology, which was developed between the DG ENER, so from the European Commission, and Energy Wheel, so the institute which is behind this study. So they have developed a methodology to figure out the needs of energy based on the NUTS-3 level, so on a quite detailed level in Europe. And they also based their calculations upon policy documents. So one was the Repower EU initiative, but they have also we also worked on a mixed 2030 scenario, so which is more somewhat modified towards industry. So these two scenarios have been used in order to calculate the energy or electricity needs of the futures. Can we go to the next slide, please? So here you see now, let's say an idea of the energy needs of the future. So today, just to give rough numbers, so today around 1,000 terawatt-hours a year are used by the industry in Europe. So 1,000, just to remember this number. And then what is projected is that around, with these scenarios, that around 500 terawatt-hours will be added until 2030. So this is the expectation. So plus, more or less, plus 50% electrical energy more towards industry in 10 years. So this is more or less the expectation which was calculated. Can you move on to the next slide? So this we can skip, it's the same information as before. And then what I already said before, so there are two scenarios which have been used for the calculation. So one is Repower EU. So what is mentioned Repower EU as assumptions have been converted into finally energy needs. And you see here numbers for direct electrification and hydrogen, syn fuels, e-fuels, and then the fertilizer, which also need quite some electricity. And then there is another scenario, which is called the European mix. And in these scenarios, there is more electricity, direct electricity use, more production of fertilizers in Europe, but the hydrogen part, so direct production of hydrogen in Europe is lower. So these are the differences. Okay, we can move to the next slide. So here is the summary. What I already said before is that compared to 2018, we need around plus 50% more in terms of electricity in industry. Here it's around 50% of this increase goes to hydrogen plus derived fuels, chemicals, fertilizers, and the other half is more or less direct electrification of processes. So this is the, let's say, the estimation which has been found by this study. Now we will move on to electricity supply. So in the next slide, having another slide. So here is still demand. So this is more or less the same information as before, but now with all European sectors. So one sector is industry with around, so in 2020, around 1,000 terawatt hours need. Then we have the other sectors which are now just put together. So it's mobility, it's residential, it's all the other sectors. And then there are also energy losses, which are mentioned here. And then there is a projection towards 2030. So for industry more, the hydrogen construction generation for industry included, and then the other sectors. So you see that the total energy need, electrical energy need, is expected to grow towards around 3,500 terawatts hours in 2030. So this is the expectation that we made here. And then, so the demand side you see here, and then on the other side, it's about the supply side. So in 2020, there is around, now I also use rough numbers, so around 1,000 terawatt hours of renewable electricity, and there is around 1,700 terawatt hours of fossil-based electricity. And in order to meet the demand in 2030, we need to increase the amount of renewable energy, electricity, and we need to reduce the amount of fossil-based electricity. So the amount of renewable electricity which is expected in 2030 is 2,400 terawatt hours, according to this study. So can we go to the next one? Next slide. So now you see the same column that we saw before on this slide. So it's around this 2,500 terawatt hours, which is needed in terms of renewable electricity. The energy European mix scenario even says a little bit more, so around 100 terawatt hours more. And then what we do here on this slide is to compare with the supply side expected according to different European scenarios. So the first scenario you see here next to the first one in yellow with 1476 terawatt hours. So this is national projection. So if we continue like we do now, then we will end up in 2030 with around 1,500 terawatt hours, and the need is 2,500. If we run with a speed of plus 50 gigawatts capacity expansion for renewable energy in electricity per year, then we end up with around of 1,700 terawatt hours additional in 2030. So and there are different scenarios which are here given, which end up with different numbers, but you should look to the last one. So there is one calculation which is based upon 100 gigawatts per year renewable electricity extension. So if this happens, then we are very close to what we should have. And there are two other scenarios which also describe that this could be possible in Europe. So you should remember that we need a capacity expansion of around 100 gigawatts per year, at least, in order to meet the electricity demand. So can we go to the next slide? So here is the same slide, but only focusing on the additional electricity demands that we need. So before you also saw the replacement. This is also here now. So in the national projections, so this is the third column here. You see this number of 440, and what we should add addition. So what we really should add is 1500 terawatt hours. And according to the national projections, we are with a gap of around 1000 terawatt hours. So if we continue like we are busy, then we end up with a deficit of 1000 terawatt hours in 2030. If you are able to move with a speed of around 100 gigawatts hour per year extension, then we could be close to what we should have. Can we go to the next slide? So these are now the let's say the conclusions from the study. Renewable electricity extension needs to increase by a factor around 2.3. So 2 to 2.5. This is really necessary. Otherwise, we will never reach this electricity supply in 2030. Then future renewable electricity supply will fall short compared to the needs for the process industry in a scenario that incorporates REPowerEU ambitions. So if you follow REPowerEU, as it said, then we will have not enough electricity available. And what I already said, so the national projections in this case, if we continue like this, then we will have a shortage of 100 terawatt hours. If we follow national plans, which are much more ambitious than the national projections of what's done, then we also end up with a shortage of around 400 terawatt hours a year. And in order to really be compliant with what we want to do, we need really this 100 gigawatt per year extensions for renewable electricity capacity. So and then there are some for the next slide. This slide here. So these are recommended measures that we gave towards Aspire organization, which means also towards the processes for planet partnership. So we know that there will be a shortage of energy, of renewable electricity in 2030. So in order to de-risk what can be done, reinforce innovation towards energy efficient material production even more. So be careful with use of electricity. Think about how to use best renewable electricity and material production. Then also strengthen effort in direct electrification. Then also think about flexibility. So on-site electricity supply, industrial processes, make them more flexible to be able to use as much as possible of the electricity which is made available at the moment that it's there. And then the others are also search for alternatives to renewable electricity or other forms of energy which are not renewable energy and use them in process industry. And the last one is about think about a global solution. So if we know that there is not sufficient electricity available in Europe, think globally and try to find solutions there. So this is what I wanted to show to you. So thank you very much for your attention. There are some additional slides in the presentation just for calculation purposes. So if you want to recalculate some values, it's possible with these additional slides. I recommend to you to look to the presentation, and if you have questions, you can always ask the person who was the most effective one in the presentation. So can you go to the next slide? So this person was the key person in order to do all the calculations for this study. Okay, thank you very much, and I wish you a nice workshop today.
Okay, thank you very much, Frans. And well, as said at the beginning, we will not have questions and answers immediately after each of the contributions, but we will have such a session at the end. Nevertheless, if questions or comments are coming up, don't hesitate to list them already in the Q&A. We can prepare then also a bit already the question and answer session of today. Okay, that brings us to the second speaker of today, which is Walter Vermeijeren from Total Energies Corporate R&D. Who will talk to us about electrification technologies. So, Walter, looking forward to your presentation.
Okay, you are seeing the right screen?
Yes, it seems so. Yeah. No, we see your slide full screen. So.
Yeah. Okay. So I'm Walter Vermeijeren. I work for Total Energies, and I will try to, let's say, to set the scene here on electrification technologies. And in this respect, you see lately that people start to talk a lot about to electrify, to decarbonize, or even a new word has been invented, electro-decarbonization, as a means to deal with climate change. So I will first start with just 2 slides on Total Energies, because our company is undergoing a real revolution lately, and this has to do with the need to decarbonize also our industry. So Total Energies has changed the name from Total to Total Energies in 2021, and the reason was that we want to help to solve the climate change problems, and the fact that there is a dual objective, which is that there is an increasing demand for energy, because we are living here in let's say modern countries, but there are still a lot of countries in the world that are still developing fast, and they need more and more energy. So the energy has to be affordable, reliable, and cleaner, and that's why we declared that our ambitions by 2050 will be that we want to reach carbon neutrality, but we are saying that this can only be done together with society. It's not one corporation who can do that alone, because that will not make any sense. So far, Total is still a very integrated company where we produce energy, we transform the energy into something that can be sent to the market, and we supply it to the customers. And what you will see is that we are moving from, let's say, a fossil-based or a petroleum-based company more to a renewable energy company. And our vision is the following on this slide. So in 2022, our energy mix was still 90% fossil, so mainly petroleum, liquids, and natural gas. And we had a little bit, let's say, more or less decarbonized electricity and some biomolecules, biofuels, and some biopolymers. We believe that in 2050 it will be completely different. So we will be a producer of 50% decarbonized electricity. 25% will be, let's say, low carbon fuels like biofuels, but also the biopolymers will be part of that. And then still 25% will be fossil-based, so a little bit petroleum, and still a significant part will be natural gas. At the same time, we are convinced that our company has to capture and store between 50 to 100 million tons of CO2 per year by that time. So we are becoming more and more a multi-energy company that is undergoing this transition to, let's say, a low carbon society. Before starting to talk about where can we electrify our industry, just an introduction. What are the 3 scopes? This has been introduced in the past by the DHE protocol, where they defined the 3 scopes just to so that corporate leaders can communicate, and they can report, in fact, what their emissions are. So we have, let's say, the scope 1 emissions that are the emissions that are related to what you have under control. So that what your process is producing. Scope 2, that is, let's say, the energy vectors that you purchase from someone else, and that has also a carbon footprint. So in fact, Scope 1 and Scope 2, this is what a company can report and has under itself control. And then the Scope 3, these are all the emissions that are coming from upstream. So buying feedstock, for instance, and all emissions related to the downstream operations. So the use of your product that you sold to a customer, that is the Scope 3. This carbon disclosure project of a few years ago, they did a survey among many companies to see what is the different contribution of these scopes for companies, and only 23% of the emissions are, let's say, Scope 1 and Scope 2, so under the control of a corporation. 45% is coming from upstream and 32% is coming from downstream. And you see this in the graph here at the right. So for instance, for chemicals, the part of Scope 3 is still very significant. It's 75%. For oil and gas, it's even much more. Oil and gas conversion is a fairly efficient process. But yeah, the fact that the customer is burning our fuels, the Scope 3 is close to 90%. So these are important parameters to consider, and that's why most of the corporations, they say we can be part of the solution provided that it happens together with society, because the scope 1 and Scope 2 of one company becomes the Scope 3 of someone else. So it's something very interrelated. So if we look to how primary energy sources are used in society and are transformed in one form of energy into another. So today we are used to use most of the time chemical energies, either fossil or biosourced. These are typically the source of carbon for refineries, for petrochemicals. It produces high value chemicals that results in the materials and the functional chemicals that we use every day. The refinery produces fuels that results in mobility, so we can be mobile. The same chemical energy is also the source of thermal energy that runs these processes for process heat, but also for the reaction heat, in particular for endothermic processes. And it provides also the heat to our rotative equipment, typically, that we have at many locations in the refinery or a petrochemical complex. And then we see let's say the emerging energy vectors that are decarbonized by nature. Either they can produce directly thermal energy that is converted in electrical energy, or they produce mechanical energy that can be easily converted into electrical. And then solar PV that produces directly the electrical energy. Now, how can industry be electrified? In fact, there are two ways to decarbonize. Either we use electricity to electroheating, directly producing heat, high temperature to run processes, or we do electrochemistry. So again, converting the electrical energy into a chemical energy, either hydrogen by electrolysis or doing electrosynthesis, where you import then CO2 or another carbon source to do let's say the electrochemical conversion. That results in e-fuels or e-chemicals. So the e-chemicals, they can substitute, in fact, the products that we use every day. The e-fuels, they go to mobility. Electroheating can provide the required energy to run our conventional processes. And also, and there's recently a lot of talk about that, why not using just hydrogen to produce the thermal energy to run our processes. So how much heat is in fact needed? So if you look to the overall energy demand, roughly 40% is used by the industry, and of this 40%, more than 50% is just to produce heat to run the process. And this is today still mainly fossil-based. And what are now the temperature levels? So 50% of the required heat to run the industry needs temperature above 400 centigrades. And there is the interest to electrify, because for low temperatures, there are a lot of other opportunities to electrify or at least to decarbonize. When we see that in particular in refiners, refiners and petrochemical complexes, you need a lot of high temperature heat. Now, with respect to the cost of this energy, there is a significant difference today. So we have Europe and the US. So the electricity cost, the euros per megawatt hour, or for gas, you see typically a factor 2 to 3 difference. So we are, if we talk about electrification, we are going to use a source of energy that is at least 2 times more expensive than we are used to use today. So this has to be considered in case you have a high CO2 price penalty, CO2 penalty. You can partially try to compensate this. Now, to come back to so the 2 electro decarbonization concepts. So direct electro heating or going via a kind of e-fuel. Just a comparison done by a consultant here. If you can use electricity directly for heating, you have overall 80 to 90% efficiency. So this is the concept of exergy. So from electricity to heat, it can be extremely efficient. If you would go through hydrogen, then you have first an electrolysis step, which is not extremely efficient. You have to compress and transport the hydrogen, which is not extremely complicated, but you need compression. That again, that's energy. And overall, if you burn the hydrogen just to make heat, again, then you have 30 to 50% overall efficiency. So there is a factor 2 difference between direct electro heating or going through hydrogen. So if you look now to the presentation of France, where one of the big issues will be, are we having the right pace to produce or to implement the production of renewable energy or electricity in this case. So this is important that we use this precious decarbonized electricity in the most efficient way. So just a word about the carbon footprint of electricity. Today, it is still very bad. If it is based on coal, we are at least at 0.4 kilograms CO2 per kilowatt hour. For natural gas, it's 2 times lower. So if you would use this type of electricity, then okay, if you convert then the electricity into heat, then you are not solving a lot of the problems, because the carbon footprint of these megawatt hours is still very high. So we need to move to, let's say, renewable, 100% renewable electricity. A few years ago, KBC has done a preliminary evaluation based on operational cost. What has to be the carbon price before someone would select a certain technology? So it's evident energy efficiency that can already be economic today. If you look to electrification compared to green hydrogen, you see the same tendency that if you would use electricity for process heating, then you need the carbon price, let's say, roughly around 75 euros or dollars per ton. If you would go through green hydrogen, it is twice as high. So this is something important to consider in the future. So if we look to, typically for a company like Total Energies, we have these temperature levels. So the highest temperature levels is steam reforming and steam crackers. And then in the refinery, a coker is high, and the rest is rather low. So electrification is probably the most opportune for high temperature processes, and in particular for processes who are endothermic. A process that is exothermic requires much less preheating. For instance, a hydrocracker, which is pretty exothermic, so your effluent comes out at a higher temperature than the feedstock comes in. So there is a lot of, if you optimize the heat exchange, then you don't need a lot of firing duty. So the most interesting conversion, these are, let's say, the very endothermic processes. So with respect to refinery, which are very complex units where there is a lot of distillation, a lot of unit operations, conversions, and so on. So some are exothermic, some are endothermic, and typically we have a lot of fired furnaces for high temperature processes and also for distillation. For instance, these atmospheric and vacuum distillation, you go above 300 centigrade, so you heat with the furnace, not simply with heat exchanger or with steam. And typically steam is then used for low temperature processes and for low temperature distillation. But we should not forget that steam is always produced in a fired furnace, so also emitting a lot of CO2. But for these operations, there are already, in principle, a lot of simple solutions. KBC did a survey a few years ago. So they defined a kind of technology weighted score. No, this was done by OGCI. So this is an association of oil and gas companies that are exchanging guidelines and opportunities on how to decarbonize our assets. So they developed a technology weighted score. So it's evident that a few are very interesting already today. So this is electrical drivers for turbines. Every time you can avoid that you condense steam, you have always very high efficiencies. Electrode boilers can be implemented today because they are known for many decades. And if you look to the amount of heat replacement efficiency, they are all very close, because you have the efficiency of a furnace. So typically with electrification, you have a higher efficiency. There are two exceptions, which is using fatal or let's say low temperature heat that is typically today not valorized. So with the mechanical vapor recompression, you have a very high heat replacement efficiency. And also if you avoid the condensing of steam, then you gain directly a lot of inefficiency. So just two last slides on the Cracker of the Future consortium. So a few years ago, we started this at the request of, let's say, the innovation ministers in the Netherlands, in Flanders and North Rhine-Westphalen. And they, let's say, to save the industry, the petrochemical industry in this region, which is roughly 50% of the European petrochemical industry. They wanted to promote innovation, and the topic that was selected by the consortium was, can we electrify furnaces that run, let's say, up to 850 centigrades. So we have, and this region is 50% of the steam cracker capacity in Europe. And if we would need to electrify this, we need 170 terawatt hours per year, which is roughly 2 times the power consumption of Belgium. It seems a lot, but on the other side, it is perhaps not that much if we see that the installation of renewable power in Europe is going pretty fast. It has to continue to go fast, but it is reasonable to decarbonize one of, let's say, the initial conversion step in the petrochemical industry, which is the steam cracking, just by electrifying that. So this consortium has done a lot of studies on which type of heating technologies are possible. So this is, let's say, the conventional one. So we have the firebox that radiates on narrow coils. So there is a transfer of heat from the coil wall to the molecules, and finally they reach a high enough temperature that they start to decompose into the olefins and aromatics. So there were, in literature, you see a lot of possibilities. You have microwave heating, radio frequency heating. You can imagine electron beam, plasma technology, cold plasmas, hot plasmas. South waves can be used to heat up molecules. So there are a lot of possibilities. So the main or the most well-known are resistive heating. They can produce infrared emission that is then conventional to a firebox. You can have resistive heating at the coil level itself. So you put just the potential on the coils. You can imagine inlays in the reactor that heat up then the vapors. And I think Gleb will talk a little bit about the electrothermal fluidized bed. So there you produce the heat on a particle, and the particle transfers that to the molecules that can then crack. And then you can also imagine inductive heating of inlays or the reactor wall of vessels. Unfortunately, all the boxes that are surrounded by the dashed lines were deemed not to be scalable for steam cracking. So a lot of the possibilities have dropped from the scheme. So what remains is, let's say, at the starting, resistive heating that is that provides a lot of opportunities, and then something that is, let's say, more disruptive is shockwave heating, which is a physical phenomenon which is very well known, but which can be easily applied in principle for steam cracking, because in the steam cracking you have empty reactors, and the advantage is that you produce the heat from the molecules. So you transfer the kinetic energy from a molecule into thermal energy. And you see that in the meantime, there are a lot of players who are active. This is all public information. All these companies are somehow involved in electrification of steam crackers. And we will see, I think, today a presentation of Cypox also that is developing a technology that can potentially be used also for steam cracking. So there is a lot happening, and we will see the next 5 years which technologies can be upscaled, because it's all about upscaling. It's not just about doing tests in the lab, but you need to demonstrate that it can run at very high performance and times. So this is, I think, a review of what is possible with respect to electrification. So a lot can already be done, because it's just about heat pumps, mechanical vapor recompression, electrical boilers, and so on. But if you want to go a step further, in particular for endothermic processes, everything has still to be developed. And that's why we are here today. Thank you.
Exactly. That's indeed what we will be working on, and then what we are working on, among other things, with the projects that will be presented in the next part of this workshop. So many thanks, Walter. And with this, I would like to move the words towards Gleb, who will present us the first project of the 3 sister projects within the call on electrified reactors, and that is e-CODUCT. So Gleb, the floor is yours. Yeah, it was fine, but we don't hear you right now. No, I think it will be your headset.
It was working before. Can you hear now?
Yeah, now we can hear you.
Okay, excellent.
Okay, all sets.
Yeah, good morning, everybody. So today I'm going to present the ēQATOR project, which stands for Fast Response Electrically Heated Catalytic Reactor Technology for CO2 Reduction. And Walter already gave a little highlight on what we are going to do, but I'll provide more details. So what is the motivation behind our project? The situation of today is that in industry, only minor amount of produced or co-produced CO2 is valorized, and there is no complete value chain on circularity of carbon. And this is why reduction of greenhouse gas emissions, it's a very hot topic. But despite there are developments on catalysts which allow direct conversion of CO2, for instance, in methanol, there is no business case yet. In other words, it's simply not economical. Society, nevertheless, still has a demand of liquid fuels, still has a demand of petrochemicals, of polymers, and this will retain in the future, which means that refining and petrochemical sector, exploration and production sector, and emerging biogas production, they will keep operating, and it means that they will have to handle acid gas. Acid gas is a common component of natural gas reservoirs. It's co-produced during refining of barrel, and acid gas is a mixture of basically CO2 and H2S in different ratios, and it will stay there. The approach which industry uses for acid gas treatment didn't change so much in last 100 years. It's still amine wash followed by Claus process, where hydrogen sulfide is burned to basically produce water and produce sulfur. There are different variations of the process, but in principle it relies on combustion followed by several catalytic sections where SO2 is reacted with H2S to generate sulfur. What is also important that existing technologies, they provide no solution for CO2 conversion as it is. Which means that CO2 is frequently contaminated. There are, of course, some exceptions. For instance, CO2 coming after water gas shift following the SMR, CO2 coming from certain streams after partial oxidation. But in principle, it's frequently contaminated, which means it should be or purified for treatment, or it has to be handled as it is. And it's a big problem. For instance, if we aim for sequestration of CO2 and it contains some H2S, we can't compress it and liquefy it to put it back into depleted reservoirs. And again, this presence of contaminants, it causes a lot of uncertainty in how much would this treatment cost. The e-CODUCT project addresses all of these challenges, and we aim to convert mixed acid gas streams containing both CO2 and H2S. And the sweetest spot for us is roughly 50-50 volumetric ratio. So this is the stream which would be potentially the hardest to tackle with existing technologies. For instance, for sulfur recovery unit treatment of this stream, we will need to import some fuel gas just to maintain flame, because so dilute H2S stream is not suitable for Claus furnace. And for distillation, it will be very high energy demand with significant reject of CO2 in bottoms of the column. We take acid gas stream, we treat it with a special catalyst adsorbent, which will allow us to produce selectively carbonyl sulfide and to remove water. So water is a side stream for us, and also it's a value for certain regions where water is becoming a scarce resource. This is why we contribute to water energy nexus economy. Then this carbonyl sulfide is decomposed thermally to produce carbon monoxide and sulfur. And these two steps is the core of technology of ēQATOR. Carbon monoxide is in principle a versatile platform molecule which could be used for instance, Fischer-Tropsch process, which could be used for aromatics production, which could be used for methanol production, and paraffins up to sustainable aviation fuel grade. In our case, we selected methanol production as a very well-known reaction, and we use a commercial catalyst with hydrogen import just to showcase that our carbon monoxide is convertible, so that we could really valorize it. And the enabling element of our technology is actually the reactor used in the step of carbonyl sulfide decomposition. This is electrothermal fluidized bed, about which Walter has already spoken a little bit. And on this slide, you could see the design of the reactor we have in place. So this will be installed within e-CODUCT project. It's already quite significant scale. So we aim to convert roughly 2 kilograms per hour of carbonyl sulfide. And to give you some sense of dimension, this reactor will be roughly 3 meters tall with all the appliances and connectors here. So the reactor is, you could see also footage of internals of this reactor operation. It's exactly the internals we'll have in the e-CODUCT project. The reactor is operated using Joule effect. It means that it's the same like home appliances where we have a heating spiral, but instead of heating spiral, we have a catalyst bed or fluidized bed where the heat will be generated right inside. As Walter has mentioned, in principle, this transformation in resistive heating, it's very efficient. So we also expect to reach high efficiency of the process thanks to use of this Joule heating effect. The feedstock in our case, it's going upwards, and the gas is creating this fluidization, which has double function. First, it contributes to resistivity, so it's an important factor to create heating inside the catalyst bed, and also it allows to reach short residence times and homogeneous heat distribution inside the reactor. What is the competitive advantage of ēQATOR technology and why we decided to select this pathway? So as I mentioned briefly, we could benchmark it against existing Klaus process, where we will first need to concentrate our acid gas, or we will need to accept importing significant amounts of fuel gas, which would mean that we'll also increase our Scope 1 emissions. Another possible benchmark is CO2 electroreduction using, for instance, SOEC technology. So just thermodynamically, carbonyl sulfide is somehow a pre-activated molecule or less stable molecule than carbon dioxide, which would mean that just to convert this molecule, we will need to import, we'll need to supply less energy compared to CO2. The other side, of course, that we could treat mixed streams. For comparison, SOEC technology is extremely sensitive to any contaminants. So any sulfur slippage to the cell, which is main contributor to CAPEX, it will irreversibly harm it because ceramics will get sulfidized and there will be physical cracks because of crystal structure change. And another important thing that we co-produce sulfur, which is in principle marketable product, and the demand is quite high. We speak about roughly 100 megatons a year, while in existing approach in CO2 electroreduction, the other side of the membrane, there is just sweep air and oxygen is vented in form of oxygen enriched air. So there is some fatal heat which is constantly lost in case of SOEC utilization. To make this project happen, we have a consortium which incorporates 9 partners from 5 countries. Total Energies is present as 2 entities, so we have a research centrum in Belgium and research centrum in Paris. And what is very important that we have very good synergies. So we have experts in materials like Saint-Gobain and material providers as well. We have experts in catalysts, we have experts in process simulation and LCA, we have engineering participants. So the consortium we have today, I think it's a great synergy to not only make this project happen, but also to have an efficient follow-up and potential implementation of this technology at larger scale later on. On this slide, you could see the PERT chart summarizing how the project was organized. So we have 7 main work packages, including 1 additional to address ethic issues. And the pilot will incorporate 2 steps. So it will be COS decomposition for production of carbon monoxide and CO valorization for methanol production, which will be installed in Slovenia in industrial hall of melamine factory. What is important that in this industrial hall, the pilot will be fueled by 100% green energy, which is produced from sawdust residues. So in our case, we could really claim that product which will generate, they could be classified as green if we apply green hydrogen. And to structure our project, we also used an exhaustive approach. So starting with R&D and ending up with business case. So the performance of electrothermal fluidized bed reactor will be used to make an LCA study and to find also operational windows where we could really achieve more than 50% CO2 emissions compared to benchmark technologies and more than 50% reduction in energy consumed. We'll have at the end a full techno-economical analysis, and we will use also industrial planning tool which will address intermittence of different renewable energy sources. If one day we will rely on solar cells or we will rely on windmills. And we'll also account variability of feedstocks, because those who are familiar with the refining industry, they know that acid gas as a feedstock, it could vary because it's in principle a final waste of refinery operation. At the end, we'll have a certification for sulfur quality and for methanol quality as a final product. And on the basis of this, Total Energies will create a business case for potential exploitation of the technology in one of our assets. Today, we already started analysis of different market shortages for sulfur, for instance, and for methanol. And there are some good scenarios which I think create a very interesting future of the technology. And this is the final slide of my presentation. Thank you for your attention, and I'm open to questions.
Okay, thank you, Gleb. And as said, of course, questions are expected or can be diverted right now in the question and answer section of the meeting. In order to keep track of time as good as possible, we will continue with the presentations. And the next one will be brought by Gianluca from SciPox on the project EReTech. So Gianluca, the floor is yours.
Super, thanks. You can hear me well, right?
Yes, we hear you well.
Super.
So I think just start sharing the screen.
Good. And you can also see my screen now, right?
Yes, and now it's in effectively in presentation mode. So all set to go ahead.
Super. So yeah, first of all, thanks a lot for inviting us to this seminar, and it's really nice to see that there are more than 100 people online attending this. Yeah, as mentioned, I'm Gianluca. My background is chemical engineering, and I am working within SciPox, and now I would like to give you a brief overview on what we are doing in the EReTech project. So, well, first of all, what the EReTech project is, that it is electrified reactor technology development. The timeline is we have started the project in June 2022, and we will be completing in November 2023. The overall budget of the project is 9 million euro, and we are having 6 industrial partners and additional 7 university and research institutions that are supporting us on the development and validation of this technology. The coordinator is the Technical University of Munich, and as you can see here from the map, well, there are 8 countries from Europe that are involved within this project. I guess we start immediately a bit on the technical side, and as also before Walter was mentioning, well, we are working with resistive heating, and if we compare a bit on the potential technology, reactor technology that you can develop using resistive heating, you can mainly identify 3 different options. Well, the first option is simply you are getting a furnace, like an oven similar to the one we are having at home, just for higher temperature, and you install inside your reactor So, well, what you are doing, you are generating the heat around the reactor and you are transferring through the wall. And in this way, well, you are having still a limitation on the heat transfer that you are also having in a traditional firebox, and you are not really able to intensify the process. Another solution would be taking a material that is electrically conductive, and you use this material as a catalyst support, and then you are applying electricity. In this way, you are using the catalyst support both as a catalyst carrier as well as an heating element. And in this way, you would be able to achieve a very high intensification. You are decoupling the heat transfer from the heat flux through a wall of a reactor. On the other side, let's say you are combining usually a metal that is an electrically conductive material together with a ceramic that is usually a catalyst. So you are having this combination that needs to be properly tuned to be able to be stable. And well, then we have another solution that is you are using a ceramic catalyst, and you are installing within the ceramic bed heating element that are in close proximity both to the catalyst as well as in direct contact with the reacting gas. This is the technology that we are using and that we are scaling up within the EReTech project. And if we look a bit more in detail on how the reactor is looking like, well, you can see that the reactor is looking as a cold skin pressure vessel that is having an internal refractory lining. Inside the pressure vessel, you are hosting an electrically heated catalytic bed that you can see here, that is a sort of a ceramic macrostructure, having hollow flow path where the heating elements are allocated. And if you look a bit more in detail and in a sort of a very basic in a very basic way, well, you can see that you are having the ceramic catalyst. You are creating a gap where the gas is flowing, and then you are having an heating element that is providing you the heat. So the gas is here flowing. From one side is heated, and on the other side is finding the catalyst where it is reacted. And this is the selected technology and the technology that we have that we are using within the EReTech project. Well, what is the advantage and what were we able to achieve before starting this? Well, we saw that it's possible to reach a temperature as high as approximately 1,200 degrees Celsius. And you can also achieve a huge intensification, meaning you are able to provide a lot of heat in a small volume. And we will be talking also later as a power to volume ratio that can be as high as 25 megawatt per cubic meter. Yeah, at the same time here, we can see what is, for instance, the performance of such a reactor when we are performing steam methane reforming. Well, you can see here a plot 1,000 hour of operation, test at 10 bar 900 degrees, steam to carbon 2. And you see that the conversion is very close to equilibrium and is also stable. The starting point of the EReTech project was this system. This is a mini reforming plant. So it is involving a 25 kilowatt electrically heated reactor. And well, you can see from this picture here we have the gas and the water supply, the steam generation on the at the bottom, the superheating of the feedstock here. Then we are entering into the electrically heated reactor. As mentioned, here we are able to provide 25 kilowatt of electricity to compensate the endothermicity of the reaction. The syngas that is here produced is going out, is quenched using water and to freeze the equilibrium to avoid the reaction to continue. yeah, we go out here and we are doing cooling and separation of the condensed water before going into a post-treatment that in this case we already needed because we are producing approximately 30 normal cubic meter per hour of syngas. Well, this was the starting point of the EReTech project. And what are the objectives are developing and validate an electrically heated steam methane reforming for mainly two applications. One application that is decentralized production of hydrogen, converting biogas. And in the other case is a centralized application where we want to decarbonize a traditional steam methane reforming plant, thus being able to have a low carbon hydrogen. Well, I guess all of you is familiar with the steam methane reforming, but maybe just a brief overview. Let's say, what is steam methane reforming doing? We are taking methane and reacting this together with water to produce syngas. This first step of the process is extremely endothermic and is taking place at very high temperature, above 700 degrees. And the step is endothermic. The second step is the further conversion of the CO with water to produce extra hydrogen. And here we are having a mildly exothermic reaction. Overall, you see that from one molecule of methane, we go into four molecule of hydrogen. And the overall process is extremely endothermic because, as you can see, approximately half of the hydrogen in a steam methane reforming plant is coming from water. How are we currently running this process? Is we are having a feedstock that is methane used as a reagent. We are having also methane that is used as a fuel to produce the heat that is necessary to compensate the endothermicity of the reaction and to reach the very high temperature. What we are getting out from the process is 1 kilo of hydrogen and 10 kilo of CO2 per kilo of hydrogen. If now we would say, well, we need to decarbonize and decrease the CO2 emission of the process, what we could be saying, well, we remove the fuel combustion. We don't burn methane, but we can use renewable electricity to provide the high temperature heat. And if this is what we are doing, well, we are able to decrease the CO2 emission and decrease this by approximately 40%. In this way, we will be going from a steam methane reforming process into an electrified steam methane reforming process. Well, it is clear that this is not currently possible. There are not technology at scale that can be applied for large system. And what we need mainly to work are actually the activity that we are trying to cover within the EReTech. And we can say, well, the first things we need to work on is on the catalyst. And the question that we need to address is if we take a traditional reforming catalyst, would we be able to use that? And would the catalyst have enough stability and lifetime? In particular, considering that if you remember what I was mentioning at the very beginning, with an electrically heated reactor, you are achieving a very high power to volume ratio, meaning you are achieving a very high intensification that is extremely positive on one side because you are having a small footprint of the plant, small capex, but at the same time, you are also able to allocate inside the reactor a very limited amount of catalyst. So you really need to make sure that that catalyst is stable and is able to have a certain lifetime that the industry requires. And this, of course, is a challenge that is now raised with an electrically heated reactor and was not in the case of a traditional steam methane reforming, because in that case, the amount of catalyst that could be allocated in a firebox was much more than the amount of active phase that the reaction really needed. Yeah, another activity that we are performing and that we need to work within the EReTech project is what will be the biggest size of an electrically heated reformer, and also would the plant be involving a multiplicity of reactor, of electrically heated reactor, or would the traditional economy of scale still apply? In particular, we know that for the chemical industry, for the oil and gas industry, usually one equipment big is cheaper compared to many and small. And also this needs to be really rethought and restudied, because what an electrically heated reactor requires is something different than what a traditional reactor needs. And then another important things we are working within the EReTech is the process. If we are having an electrically heated reactor, how is this integrated in an overall hydrogen plant? What are the modifications required? Balance of plant, utilities, steam generation, steam production. And also, well, what are the standard and the conformities that the reactor and the process needs to follow to be able to have a safe installation, as well as what is the real life cycle assessment, what is the real CO2 emission that an electrically heated reactor in a hydrogen plant is able to achieve. Well, we are addressing and trying and working on addressing this question with the consortium, and the consortium is, as mentioned at the very beginning, involving 50-50% between industry and research and university, and we are covering the whole value chain. So from the technology development and catalyst development up to the final commercialization of the hydrogen. And yeah, you can see here an overview that we are also following in the consortium structure, two main paths, that is how can we address a decentralized hydrogen producing plant, and how do we address a centralized plant. Well, within the EReTech project, we are mainly installing two pilot plants. The first pilot plant we are currently completing, and it will be started up in April 2024. In this case, we are involving an electrically heated reformer of 250 kilowatts. And we are stopping at the syngas production, mainly because we are using this pilot for the ESMR scale-up validation, and also for getting the data that we need for the process simulation and for the development of the process. Well, here you can see a picture of the plant, and this is all contained in a 40-feet shipping container. The second plant is a complete hydrogen producing plant. It will be producing 400 kilo per day of hydrogen, fuel cell grade hydrogen, and this system is supposed to be installed in a biogas plant and started up in March 2025. And yeah, with this, we want to prove that it's possible to directly convert biogas into hydrogen, as well as validate the business case on decentralized renewable hydrogen production. So just my last slide, just to show what is the impact of the EReTech, what are we trying to do. And also we heard from the very beginning of this seminar that the availability of renewable electricity is limited, and we need to decide, at least for now, where we should be putting the renewable electricity to achieve the highest decarbonization level. And if we look, for instance, at the hydrogen production, well, we know that currently most of the hydrogen is produced using fired steam methane reforming. There is no usage of electricity, and per each kilo of hydrogen produced, we are also emitting approximately 10 kilo of CO2. We know that the final target is having a system that is fully decarbonized. So we know that we want to go, for instance, for electrolysis. We want to have 0 CO2 emission per kilo of hydrogen. But if we immediately go in this way, well, we will need per kilo of hydrogen produced approximately 50 kilowatt hour of electricity. And of course, we are decreasing by 10 kilo the CO2 emission. If now we go for an electrical heated steam methane reformer, we need 14 kilowatt hour per kilo of hydrogen, and we are still emitting 6 kilo of CO2, but we have avoided 4 kilo of CO2 per kilo of hydrogen. And since the amount of renewable electricity is limited, well, we need to decide if we should put the renewable electricity here or here, meaning, do I need to use this in a process that is achieving the highest CO2 emission reduction, as long as I don't have enough renewable electricity that is enabling me to go for something else and for something that is less effective in decarbonizing the hydrogen production. Yeah, with this, I am done. Thanks a lot for your attention. And if you have any question, we'll be happy to answer at the end of the whole presentation.
Okay, many thanks, Gianluca, for your very nice presentation. Some questions are indeed already appearing in the chat, so you can prepare some answers already. But I would say, do not spend too much time on answering and discussions right now. Keep our attention to the presentations. But on the other hand, to the audience, don't hesitate to write some questions already. It can only help in preparing the answer and the question and answer section afterwards. Okay, last contribution before the break will be from Richard Hein from SINTEF on the ēQATOR project. So Richard, looking forward to what you will tell us.
Thank you very much, Joris, for the introduction. Philippe, you're showing the slides, right? Yes, very good. So yes, as Joris mentioned, my name is Richard Hein. I'm the project coordinator of the ēQATOR project, chief research scientist at SINTEF in Oslo. If you could go to the next slide, please. Here is all the dry information. This project is reaching its halfway point. We started in June 2022. Project budget of around 8.5 million euro with a grant of 7.5. And then you see the logos of all the partners. There are 15 partners involved in this project, of a wide range of partners from RTOs and universities through SMEs into larger companies such as Equinor and JM, Walter Tosto, and NextChem. Next slide, please. It's important, I think, to present a vision for the project. And I'm a chemist, and so as opposed to what Walter had introduced earlier about this concept of electrodecarbonization, you can't, as a chemist, I think that's a very odd term to talk about decarbonization, because for chemicals, materials, you can't decarbonize them. They all contain carbon. You have to get that carbon from somewhere. So whereas energy can be decarbonized in that you can stop using fossil fuels to make the energy, chemicals and materials must be defossilized, meaning that you have to get renewable carbon as your source for your chemicals and your materials. And if you're going to do renewable carbon, then you have essentially three vectors that you can look at. You can look at CO2, you can look at biomass, and you can look at recycled carbon materials such as plastics. And in essence, in the future, we have to get carbon for our chemicals and materials from the carbon that is already above the ground and not from the carbon that is below the ground. And in this respect, biogas is a very attractive source for renewable carbon. It has about a 50-50 mixture of methane and CO2. It comes from various sources. You have agricultural sources, you have urban sources. But the issue with biogas today is that it's only used for energy production. And so that the biogas the methane is separated out, the methane goes into the grid, the CO2 is emitted. So whereas there is a climate benefit from doing that, you're still emitting your CO2. And so what the ēQATOR project wants to do is it wants to utilize biogas for chemicals production, specifically methanol, in the idea that you'll be able to defossilize some of this methanol production and promote the development of local methanol economies. Next slide, please. So methanol is, as many of you may know, is an important base chemical. It has a large global market size. It's a starting point for fuels, a number of different chemicals and polymers, and a world-class methanol plant produces around 3 million tons each year. And our goal is not to replace these large-scale world-class methanol plants. What we would like to do is we would like to try to make methanol on a smaller scale and more locally. And the benefit of this is that methanol today is produced by steam reforming of natural gas. So you do a steam reforming of natural gas to syngas, which is a mixture of carbon monoxide and hydrogen, and then you make the methanol. And the emissions from making that syngas today account for about 10% of the CO2 emissions from the chemical sector. The only exception to the large-scale methanol production that takes place today is you have a CCU approach, for example, Carbon Recycling International up in Iceland, and you have around 0.2 megatons of renewable methanol produced each year. Next slide, please. So the project objectives for the ēQATOR project is to make syngas from the dry reforming of methane rather from the steam reforming of methane. Now, this is a more difficult reaction in that the catalysts that you use for the dry reforming are very much more prone to coking. But this is also an endothermic reaction, just like steam reforming of methane, so you can use electricity to do so. And what we aim to do in the ēQATOR project is to show at TRL6 and a scale of around 10 cubic meters per hour of biogas that we can do this dry reforming of the biogas to syngas and then to methanol. The methanol production will not be part of the TRL6 demonstration, but what we'll do is we will take the products that we observe from the electrically heated catalytic reactors to make the syngas and do the methanol synthesis separately. The project will be looking at two different ways to do the electrical heating. We'll be looking at microwave heating and we'll be looking at resistive heating. And the innovations that we expect from this project involve catalysts that do not coke. That's very, very important if we want to have a sustainable process. Optimized reactor design for efficient heating, and the an optimized global process design for the efficient integration of the up and downstream processes. If you go to the next slide, please. So as I've mentioned, catalyst coking is very important. It needs to be minimized and avoided to the amount possible. And what we've done is we've developed two different processes to look at that will minimize our coking potential. So we have what we call a dry reforming process, which is simply methane and CO2, which starts from a biogas composition, which is like that you get from the making biogas from the organic fraction of municipal solid waste. We have a second process that we call the mixed reforming process, where water is added. We expect that to be a less risky proposition, but that mixed reforming process starts from biogas composition that is produced from agricultural residues. And what we've been able to do is we have a catalyst composition that shows the minimal coking with the dry reforming gas mixture over 100 hours. So on the left-hand side, you see the stable CO2, methane and CO2 conversions, and we have a syngas ratio of about 0.4. And on the right-hand side, you see the coking profile of the catalyst after the reaction, and essentially there is no coking that is observed. So we have a very good starting point in order to have a catalyst system that we can integrate into our electrically heated reactors. So how do we do that? And I'll just show the examples for the resistive heating on the next slide. On the next, yes, thank you very much. So for the resistive heating, we will be having coated honeycombs. These are electrically conductive honeycombs. The catalyst will be wash coated on these honeycombs, and then these honeycombs will be coupled with electrodes, a fiber mat, and a metal housing. And what we'll be doing with these honeycombs is we'll be setting them up in sequence so that we can have a parallel set of honeycombs that can be individually steered for the temperature, so that we can control the power and the heat that goes into each honeycomb in order to match the reaction kinetics that we need to make the most effective synthesis gas. And that is shown on the slide on the figure on the right-hand side, where we have a modeled schematic temperature profile and conversion over this cascade length, where we have multiple honeycombs set up in parallel. At the bottom left-hand side, you see a nice picture of how this works, so that one of these honeycombs can be heated without any issues up to 1100 degrees, and that the temperature is achieved within a minute or so. Next slide, please. So the key impacts of this, as I mentioned, the steam reforming of natural gas to make methanol has a very high CO2 footprint. It's about 10% of the CO2 emissions from the chemical industry, and we expect to save 60 to 80% of the carbon dioxide emissions from that methanol synthesis with our technology. We expect around 7 megatons of CO2 per year up by 2030, and up to around 45 megatons CO2 saved per year at 2045. Because we're doing this electrically, and has been commented before, we expect higher capacity conversions, we expect more compact reactors, we expect higher energy efficiencies, and we hope to have, we have these novel optimized catalysts already in-house for this biogas valorization to methanol. Next slide, please. So as I stated, we aim to have a TRL-6 reactor in place, demonstrated by the end of the project in November 2025. We will be demonstrating both the resistive heating and the microwave heating with these two different gas mixtures. We'll be doing, so essentially there'll be 4 pilot campaigns run in the pilot plant. We'll be doing the dry reforming with both the resistive heating and the microwave heating, and then we'll be doing the mixed reforming with both of the heating technologies as well. We'll be having a 10 cubic meter per hour feed, doing it for 1,000 hours, which is roughly 7 weeks, I believe. And then the methanol production step will be done on a modeled gas from the syngas compositions we get out of the reactors. We expect a full-scale plant to have a feed of around 500 cubic meters per hour. And one of the things that we're aiming to do with the TRL-6 reactor design and construction is to have a material selection which allows upscaling without having to do a re-engineering. And also the parallel reactor confirmation allows us to upscale this technology very readily, depending on the amount of gas that we need to implement. So the next step, assuming that, of course, this project will be successful with a positive economic and environmental outlook, we would need to do a combined reforming and methanol production at say 100 cubic meters per hour scale. Next slide, please. I'd like to thank the European Commission, of course, and I'd like to thank the ēQATOR consortium. I'm just the coordinator. I haven't done anything apart from to send in the deliverables to the Commission and coordinate the work. So thank you very much, and looking forward to the Q&A at the end.
Okay, thank you very much, Richard, for your nice presentation. So we had scheduled a short break right now. We are running also a little bit behind, but nevertheless, I think it's good to have a quick sanitary break or whatever, or take a coffee. I would say, well, let's just do that and reconvene in 5 minutes. So at 10:35, let's say within 10:35, 36. We will start with the next presentation of David Farussin of the Titan project. So see you in a few minutes from now.
Joris?
Yes.
Hello.
Right before we were seeing the presenter screen, so it's not the we were not seeing the slide.
Yeah. Let me, let's say if I do like this, is it correct or not?
Yeah, like that, it's the good one.
Okay, so I will not move from here. Okay.
Yeah. Okay. Fine. Well, David is there, and the people I encountered here in the corridor were also going back to their computers, so I think we can slowly get started again. So we still have 2 projects to go. The first of that is Titan, which is coordinated by David Farussin. And well, David, looking forward to what you will tell us about Titan.
Thank you very much, Joris, for the invitation. And I think to put all these projects together. So I will present Titans, which deal with the direct biogas conversion to green hydrogen and carbon materials by microwave heated reactor. And well, we will mention very briefly the use of the carbon for soil amendment. So the project has started in September 2022, and it's a 48 months project. So in a nutshell, objectives are to develop an innovative microwave heated reactor. For the direct conversion of biogas, it means that we will not separate the CO2 from the methane into hydrogen. You can see the sketch a bit here with the, waste, for example, or agri feedstock to go to the biogas plants with the digesters, and then ideally it would go to the microwave catalytic conversion to produce hydrogen, and this hydrogen would be converted to electricity or to chemicals. And one of the ideas for the circular economy is that the carbon we would produce would go back to the soil for amendment. We aim at producing a hydrogen high yield and also to reduce capex, because we believe that it would be a bottleneck for the deployment of this technology, particularly in the agri sector. So the basic concept is to use the feedstock methane and CO2 from the biogas, and to combine, I would say, the methane cracking together with the methane dry reforming, because that should allow combining these 2 reactions should boost the hydrogen yield by the use of a post water gas shift reactor. We also want to aim only at very, very high conversion, close to the thermodynamic equilibrium, in order not to, let's say, use PSA gas separation for like hydrogen and methane as a post-treatment, because it would have an extra cost. and previous project concluded that gas separation, either CO2 methane or hydrogen CO2, were very costly and really penalized the world economics. We want to look at scalable microwave reactor. I will have a slide on that. And we want to have a global process point of view, I would say. Basically, we claim that eventually we would have a negative emission solution because obviously the carbons come from biomass, and here as the technology will not produce any CO2 because the carbons will be stored as a solid carbons, and which would make the global carbon pass negative. And we want also to use abundant and non-toxic catalysts, particularly because we want to recycle the carbon into other materials or for the fertilization the soil. So here are, I would say, very first results. First we have, let's say, screen catalyst in conventional heating reactors by electric heating using a model biogas fixture of a 2-to-1 ratio, and we use iron-based catalyst, very cheap, good fluidization because we want indeed to look only for fluidized bed. And what you can see on the top is the conversion of CO2 and methane, which are very depending on the temperature. And basically, we can go to almost thermodynamic equilibrium, only about 900 or 950 degrees C. And if you measure the carbon balance, actually you can see that at higher temperature than 900 degrees C, there is the methane cracking occur, and you produce the carbons. You will see that in the next slides. Whereas if the temperature of the reactors is below 850, then the carbon is gasified by the boudoir reactions, and you produce carbon monoxide. So it's anyway crucial to operate at high temperature for thermodynamic, I would say, point of view, and to produce the carbon. So you can see here on this video, I hope you can see it, a fluidized bed working at 900 degrees C with the iron-based catalyst, hot, very hot, in fact, like a lava. And we do not see, I would say, the activation after 2 hours of on stream, even maybe 3. Actually, we achieve thermodynamic equilibrium, and we produce about 30% yield of carbon, which at the end of the day would make an outlet of 60% of hydrogen, 30 of CO, and very little methane and CO2. So basically, you will produce a syngas with a 2-to-1 ratio, and you will produce at the same time carbon by 0.3 kilograms per kilograms of catalyst per hour. You can see the the size of the bed before and after 3 hours. So you can see you really produce and store the carbons, while some have been, let's say, collected on the top of the reactor. And that would mean that with this outlet stream of 2-to-1 ratio, you could think about another catalytic process, so namely the Fischer-Tropsch, to produce hydrocarbons. So basically, you can think that with only, I would say, 2 catalytic steps, you could go directly from biogas, of course, with some purifications, but I wouldn't say with gas separation. With 2 catalytic steps, you could go directly from biogas to liquids, hydrocarbons you can either use or transport. So in contrast to maybe, you know, the classical, I would say, methane reforming or dry or steam reforming, here really what we want to do is coking. So coking is more an ally than an enemy. Of course, we have to collect the coke and then use it. And the value of the carbon which would be produced is very important for the whole economic of the project. And the market of the carbon has very different specifications depending on the applications. And there are many types of different carbons, and we let's say characterize various carbons, including our carbon, and we figure out that the carbon we produce is of the class of what they call turbostratic, which is amorphous but still organized. It is not a graphite, but it's in between amorphous and very crystalline graphite. And for that, there are some applications. There is a but. The but is that, of course, the carbon we produce is contaminated by some iron, and that has to have consequences on the market, of course, and the value of the carbon. On this slide, you can see a typical microwave heated reactor technology with a fluidized bed. So two of this kind are installed in Warsaw University and at EReTech in our office. So we typically have a 915 megahertz solid state generator with a waveguide and cavity from Muge. You can see here. Yes, I will talk about the temperature control, and we have so fluidized columns with collectors. It is important in view of the upscaling to look at the microwave technologies. So we have by choice selected 915 megahertz because it's more commercially available at larger size. It also allows a much larger reactor size than the conventional, I would say that here, that the 2450 megahertz, and also in a wall, the 915 megahertz technology is more energy efficient than the more conventional one we know from our kitchen. Would you have questions here? I think Marilena Radoiu from MTC Technologies, I think, should be present here and could provide you more detailed answer to the microwave technology. That is, of course, key in our project. We have to face a major challenge in the upscaling. This is really the upscaling of the lab reactor to the, I would say, demonstrator reactor, because this is not linear. Basically, the heating is not linear because the fluidization depends obviously on the volume flow, which depends on the temperature of the gas phase, which depends on how good the catalyst and heating, and thus on the microwave absorption, and which depend where is located basically the particles and on the fluidization. So basically, you can see that everything is dependent, and the temperature control in microwave reactors is particularly difficult. You cannot use a thermocouple, and for that we have implemented a pyrometer, which of course monitor the temperature along the bed, on all the bed, and then control the power of the microwave system. So you can see here fluidizations of our catalysts in a small reactor in the microwave reactor, and you can see that with this monitoring and control of the power by a parameter, you can really well control the temperature of the bed. Yet this is at lab scale, and for increasing the scale of the reactor, because we want to make a demonstrator, we have to do a modeling of all of that, the hydrodynamics, the heat and mass transfer, the electromagnetic field, and the kinetics, in order to, let's say, design a reactor for the pilot demonstration. So here is the path we propose to the Commission for TLF5, where we are basically today to 9. I think it's a bit too much details here. I think what is important is that we will we consider 2 scenarios, one small scale biogas plant and one large scale, because they have different advantages and constraints. And we believe that all the process put together will be very different. Like possibly for the smaller plants, we may envisage like a Fischer-Tropsch reactor, whereas for the largest, maybe hydrogen can be used on site, for example. With that, I would like to conclude and to mention 2 key conferences where you may present your results or contribute. Of course, the first, it would be in July in Lyon. This is the International Congress on Catalysis. Unfortunately, the abstract mission was closed in December, but there would be talks on methane reforming and the new ways of activations of methane. But you can still apply and submit an abstract to the 3rd International Conference on Unconventional Catalysis, Reactor and Applications, chaired by Andrzej Stankiewicz from Delft and now Warsaw University. So there will be sessions, I think, on our topic. With that, I would like to thank you. Here are the partners. I mentioned Warsaw University, also Marilena from Microwave Technology. We have EBA as well, University of Hohenheim for the carbon characterizations and for the soil amendment properties, PDC for the technico-economical assessment, and the company ESD for the use of carbons in silicon carbide materials. And I encourage you to visit our LinkedIn page. I thank you for your attention.
Okay. Thank you very much, David, for presenting us the Titan project. And last but not least, I would say we have Professor Patricia Benito from the University of Bologna, who will present us the storming project. So also looking forward to that presentation.
Okay, thank you very much. Can you hear me?
Yes.
Yes.
Right now,
okay.
we don't see it in presentation.
Yeah, I'm trying to put in presentation. Right now is fine.
Yes, there is still just the bar at the bottom of the screen.
Yeah.
But, okay, it's.
I don't know why this.
Yeah, I think it will work. Even with that bar, it will work.
Yeah, I hope so. Okay. Good morning to everyone. Thank you very much for the invitation to participate in this workshop. So I will present you the technologies that we are developing in storming. Storming stands for structured and conventional reactors for CO2 methane catalytic cracking, and it was funded in the same topic than Titan, methane cracking to usable hydrogen. Moreover, we also got additional, we were granted also by the wider call to include a hop-on partner in the consortium when the project was started. Storming started the 1st of September of 2022, and it will last 36 months. We have a budget that is a little bit higher than 3 million euros, and to which we have to add the budget for the UK partner. We have a highly complementary and interdisciplinary consortium that is made by 3 universities, 3 research institutes, among them the Hopon partner, 3 small medium enterprise and 1 non-profit organization, and they are localized. So we are localized all over Europe. So we are working in the decarbonization of the hydrogen production by biomethane decomposition. And we think that this process can be considered as a bridge between steam methane reforming and water electrolysis, or can be considered as an alternative to steam methane reforming coupled with CCS. This is because of something that already David anticipated, is because of in this reaction we can produce very pure hydrogen in the gas phase while capturing the carbon as a solid. So we are avoiding the emissions from the reaction and at the same time producing a valuable product. But the added value will depend on the type of carbon. So we can produce carbon black, amorphous, so move to other more crystalline and more valuable structures. What is the situation of this process after intensive worldwide research? Some pilot and commercial plant have been deployed. So we can avoid the clogging of the reactor and easy separate hydrogen and carbon by using moving bed, plasma, and liquid bubble column reactors, but all of them only produce carbon black. So to produce graphite or other crystalline materials, we have to have a look on the hazard and high commit processes that are those that use a catalyst. So this is because with the catalyst we are able to control the nucleation and the growth of the carbon, leading to ordered materials, but that will depend on the reaction condition and on the catalyst. So changing the type of catalyst for carbon, cobalt, iron, and nickels, we can produce graphite, nanotubes, plates, nanofibers, or other or even graphene materials. But as already anticipated in some of the early presentation, producing a solid or generating carbon is the reaction that we always want to avoid when using when producing hydrogen from steam reforming, and this is because of carbon has a twofold deactivation effect. So it will deactivate the catalytic sites and it will clog the reactor. Moreover, this reaction is less endothermic than steam methane reforming, but still we need to reach high temperatures to achieve a high conversion and in turn a high hydrogen productivity. So we will have also to deal with the heat transfer. What we are doing in storming, considering the state of the art and also the challenges, is to develop breakthrough structured catalytic reactors that are powered by renewable electricity to simultaneously produce CO2-free or CO2 negative in case of using biogas hydrogen, with a high quality, together with high quality carbon nanotubes. All of this in a continuous technology that could be deployed in a sustainable manner. So more in particular, what we are doing is designing and developing catalysts and catalytic reactors that are operating in a continuous mode with maximized efficiency. We are focusing in the production of captured hydrogen, so on-site production. And the reason of using carbon nanotubes is because they are the economic credit that will reduce the cost of hydrogen. In particular, we are working with parallel reactors operating in a cyclic mode. So we are switching the feedstock feed and the regeneration agent between both reactors. We are, besides our core technology, we are considering all of the value chain. So from the purification and separation of the biogas to the purification of hydrogen. In phase of proposal, we also propose natural gas, but after the geopolitical changes, we decided only to focus on biogas. So the technologies are earlier stage breakthrough catalytic technologies that are powered by renewable energy, and our aim is to overcome methane catalytic cracking challenges and match with the final hydrogen application, but also with the supply of renewable energy, and be easily and quickly scalable to produce hydrogen at a low cost. The reason that we are here is that we are also using electrified reactors to improve the heat transfer. And in storming, we are currently comparing 3 complementary structured catalytic reactors. We have the dual microwave and induction heating. So we will generate the heat by passing a current through a resistive material, by the selective dielectric heating of catalytic materials, or by the selective heating of ferromagnetic materials. So we have 3 different ways of heating, but we chose all of them because of they show common advantages. So our aim is to directly heat the catalyst in order to decrease the temperature gradients and heat losses, and at the end increasing the heating efficiency. And all of this with a quick startup time. We are using these structured catalytic reactors, and what are they? We are preparing and we are designing 3D engineering structured materials that with above properties, and these properties are not only catalytic ones. We are preparing the materials by 3D printed, that is guided by computational fluid dynamics, to have devices that are with an advanced design, easy production, and high adaptation. The key that we are trying to achieve is to combine geometrical parameters and composition to, first of all, have the right heating, so rad resistance, the dielectrical properties or ferromagnetic properties, but also combining with low pressure drop and a mechanical stability that is very important because we are generating a solid inside the reactor, and also heat and mass transfer. And all of these parameters will determine the activity. But we have to consider that this process follows complex dynamics because we are modifying both the gas phase and the solid phase composition. And these modifications are taking place both within the length of the reactor and the time on stream. So what about the catalyst? We are also using, like in Titan, iron-based catalysts, because like nickel, they are able to promote the carbon nanotubes growth, and because of they are non-toxic and easily available. And for us, another advantage is that they are more active and stable than nickel. So considering the endothermicity, it will be possible to reach high thermodynamic equilibrium values. But we are sure and we know that the catalyst deactivates. So a key is to find a treatment able to regenerate the catalyst and to harvest the carbon nanotubes, avoiding by a waste-free method, what we call chemical scissor protocols. This is base research that we are performing by the combination of ab initio computational methods, model catalysts, and also in situ and operando characterization. So we hope that the research that we are doing in storming will help to have a positive impact in the production of hydrogen in comparison with steam methane reforming coupled with CCS. And this is because of switching to the renewable energy and using the electrified reactors will improve the energy efficiency that can be around 60% and even higher if we consider carbon nanotubes with 100% selectivity. Moreover, we are using structured reactors, so process intensification, smaller reactors able to operate under transient conditions that are determined by the supply and demand requirements. All of this avoiding greenhouse emissions because we have the electrified reactor and we are capturing the carbon as a solid. And with a 10% decrease in the cost than steam methane reforming coupled with CCS. We have some ideas on what can be the application of the hydrogen. So this could be used in hydrogen refueling station for trucks. And we can also contribute to decrease CO2 emission for hard-to-abate industry. One possibility could be to replace methane in high-temperature heat combustion ovens for the tile ceramic industry, but also for a small-scale application of hydrogen, such as in the brightening of steel or in the tin bath for the flow gas. And last but not least, also in the chemical industry for small plants of producing ammonia. But what about with the carbon nanotubes? In storming, we are producing multi-wall carbon nanotubes, and we are focusing in their application for batteries. This is because the efficiency of energy storage can be increased, but also because at the same time we can replace graphite, that is a critical raw material. So at the end of storming, we will validate one of the most promising catalytic technologies. So only one will achieve the TRL 5, and we will perform a sustainability assessment, including economical, technical, and environmental aspect. The vision of the Storming Consortium is that the technology could be in the future be a scale up until reach the establishment of the deployment or a small or a medium scale hydrogen production plant. To achieve, to follow the pathway to this higher TRL, for sure we will need to design and build demonstration and small plants directly feed with biogas, because currently we will, or at the end of storming, we will only feed synthetic biogas, and optimize the parameters to produce high quality hydrogen and carbon nanotubes. But also, if we have a look on the mass balance of the reaction, you can see that we are producing 3 times the amount of the mass of carbon nanotubes than the mass of hydrogen. So our aim is that during the storming and beyond is to foster the carbon nanotube market. Currently, this is a niche market, a small market, but this is not related because of the properties of carbon nanotubes. Indeed, they have outstanding properties, but because of their high price. So to go beyond in this pathway to a higher TRL, we should catalyze the carbon nanotube market, decreasing the price of the materials without decreasing the quality. So fostering the application in markets such as the batteries, storming, and also in other sectors such as composite or the cement. So just want to thank to all the consortium for the work that they are doing. If you want to know more about the storming, stay tuned in the social media, in the website. I'm also available for some questions.
Okay, thank you very much also for this last final interesting presentation, Patricia. And well, I hand the word now to George, who will chair the roundtable discussion among the people that have been presenting.
Yes, thank you very much, Joris. I think that we have attended some very interesting presentations today, very informative for me as well, that I've been working as an academic person in this field, and I'm sure they were very informative for the audience as well. So some very good examples of electrified processes that can be used to intensify, process, and valorize important molecules such as methane and CO2 have been presented. If I am to summarize the common ground of the project presentations, I would say that there are 2 common elements, in my opinion, in all presentations. One is the fact that we're talking about electrified technologies. These are combustionless technologies, so we don't need to burn the fuel to create a heating medium in order to heat up the process gas. We heat only one medium, what needs to be heated. And this potentially can be translated into energy savings and, of course, reduced CO2 emissions. And the other common element is that these technologies, essentially, what they do is to intensify energy transfer. And this creates opportunities for process intensification and better performance. So these are the two, I think, advantages of the electrified technologies that were well highlighted today. But there are also some challenges related to uniformity of heating using these technologies, to scalability. And I also think that some aspects related to how do we define better performance and with respect to what benchmark should be discussed in order to further promote the movement of these technologies to higher TRLs and eventually to commercialization. So I would like to start with some questions to the presenters on the aspects that I just mentioned. So performance, scalability, CapEx, OpEx, to highlight advantages and challenges for further research. I'd like to start with the Titan project, actually. Although my questions, of course, will be relevant to ēQATOR project and Storming project as well, because the chemistries are the same, and also microwave technology is a common, and joule heating is a common ground in these projects. So basically, attending the Titan presentation, what immediately attracted my attention is the fact that it seems that using microwave technology, we can treat the flow rates that are presented. I don't know whether David is available, if he can show the last slide of his presentation to see the throughputs that are mentioned there.
No, David would be substituted by Marilyn, if I remember correctly. I don't know whether you can also...
I can mention the numbers.
Whether you
so
have the presentation. Yeah.
Validation of the technologies are meant for, let's say, large scale. I've written down biogas plants treating 500 cubic meters per hour of biogas.
Yes. Yeah.
Yeah. So after the presentation, I mean, doing some quick calculations, actually, assuming that 2/3 of it is methane, and assuming that 1 cubic meter of methane is approximately 44 moles of methane. If we are to dry reform these flow rates, the power that is needed only for the reaction itself is close to 1.5 megawatt. And I'm not counting for the sensible heat or potential losses in the hardware itself.
Okay.
So, Marilyn, I'm very glad that you're here. As you know, the most powerful magnetron available is 100 kilowatts at present, or a little bit higher. So how do the consortium members see scalability of the technology, considering these numbers? And what do they mean in terms of CapEx as well? Because I understand that you consider CapEx to be low, but can you further elaborate on that a little bit?
Yes, I mean, we have chosen, that's the first important information, we have chosen to start directly with 915 megahertz as a frequency, microwave frequency, because that allows us to go towards something like 100, 120 kilowatts today per unit, per microwave generator, magnetron, as you mentioned. We will also keep an eye, and that is also related to the efficiency, electrical efficiency of the 915 megahertz, which is much higher than 2.45 gigahertz, as David mentioned. We also keep an eye on solid-state generators, which are today are provided at higher and higher power, but obviously we won't discuss for the time being the solid-state generators. There is still a little, way to get to high power solid state generators with good electrical efficiencies. So let's talk about magnetron generators. The idea is to provide modules, you know, as long as microwave generators will be available around 120 kilowatt per unit, we will be able to provide modules. So you mentioned 1.2 megawatts. So that means, if I calculate correctly now, how much that mean? 10?
More than 10, and this is for the heat of reaction
like
itself. In principle, you need more energy. So what's the
scale-up
approach? Is it numbering up? Is it another approach?
Exactly. So the idea is, and it's not just for this project, other projects, they are doing very similar. So if we believe that microwaves will help that, then it's the idea of modular aspects, either one reactor, multiple generators around it, or one reactor, one generator. So it's in this idea. Now, CapEx probably, it's not, in terms of CapEx today, the technology is used quite a lot in diamond production. So we expect that CapEx will go down with, you know, increasing of that market. So it's also about, you know, where the microwave generators, there are the same microwave generators which are being used for diamond manufacturing. So we are expecting the CapEx to be lower with time. Okay, but once again, we are also keeping an eye on the OPEX, operational cost, and we are also keeping an eye on heat recovery. So if you know, let's forget the endothermic reaction here and exothermic reactions. No matter what, you know, if you use 100 kilowatt microwaves, we have shown a little calculation of electrical efficiency of the generator that we need about 120 kilowatt from the mains. Okay, so generally speaking, what is not taken into consideration when using this kind of microwave generators is that we have to recover all that power. You know, most of that power is not lost, so we'll have to recover and reuse it. For example, I give you an example, and this is what we calculate also in preheating the raw gas, the biogas, in preheating certain things. So I stop here.
Okay, so you see the technology as being scalable to megawatt range, let's say, yeah. Okay, well, the technology will also be studied in the Storming project and in the ēQATOR project. So Patricia and Richard, how do you see in your consortia scalability of this technology? What's your approach? Richard, you mentioned that very readily. You think that the technology can't be scaled up very readily. I jotted that down. Is that how do you see that?
That's for the resistive heating technology, using the electrically heated, electrically conductive honeycombs. I purposely didn't say anything about the microwave heating because it's too early for us to comment on the scalability, the reactor design, etc. So I unfortunately I have to sort of can't answer your question regarding the scalability of the microwave heating system. But the resistive heating system, since we're designing it in such a way that we have these individual honeycombs that can be placed in parallel to the extent that we want to place them in parallel, it's scalable in that respect. And then you could say, okay, if there's a limit to the number of reactors you place in parallel, then you just add more another stream of reactors, right?
And since, I mean, getting into a little bit to the chemistry itself, the major bottleneck of methane dry reforming is essentially, as you mentioned, it's coking of the catalyst. equilibrium conversions are very high, close to 100%. They can be reached with different catalysts. It's a reaction that has been well studied. This has been demonstrated in the literature in plenty of papers. The main issue is catalyst coking. Do you think that you can address this particular problem with either of the two electrified technologies, at least to some extent? Or this is just a materials problem, we need better catalysts?
Sure, but again, it is focusing more on resistive heating, since that's the
sure,
more
also
mature of the two technologies. We have this catalyst system that in a traditional reactor does not show any coating for. I didn't show the data, but we've run it as far as 300 hours without any significant coating. The wash coating of that catalyst onto the honeycombs is something that we're working at the moment. So under the presumption that you can wash coat these honeycombs and get essentially a high quantity of catalyst, there shouldn't be an issue on the coking aspect of this. But again, that's something that's the sort of what we're working on right now.
Mm-hmm.
And I can say that these electrically conductive honeycombs have been produced, have been reproducibly extruded. I think one of the MCI, the partner who's working on this at the moment, has like 100 of them that have been extruded by Johnson Matthey. So it's in that respect, it's a reproducible, scalable concept. We just have to put all these reactors in parallel and see what we get out at the back end.
Okay. Do you see any potential improvement in the throughputs of your process? Usually when we intensify heat transfer and we bring the process to the kinetically limited regime, then we can increase the flow rates and get higher throughputs, get higher productivities. Is this one of the goals to?
No, indeed, we want to
compared to
minimize the number of
heated reactors.
Yeah, but we don't have full kinetics yet for me to answer the question as to what extent we'll be able to have this the efficiencies you're asking about.
Mm-hmm. And regarding resistive heating, are there any challenges with respect to power losses, to scalability? Is it to uniform distribution of the current over the monolith? What's your opinion about this technology?
I'm cautiously optimistic. There don't seem to be any significant losses over the monolith. One of the nice things about it is that we can use these monoliths also just to heat gas. We don't have to coat the monoliths with the catalyst. In one of the slides I showed we have actually 3 sections that are simply just to heat the biogas that is going into the reactor, not actually doing the chemistry. And since these honeycombs can be individually controlled, it's not like you have to heat, let us say you have 10 honeycombs in parallel. You don't have to heat them all to the same temperature. You don't have to give them all the same power. They can be individually controlled. Then we have a lot more flexibility with respect to the kinetics of the reaction, how much gas goes through, what our end products are. So, but that's all to be worked on at the moment.
Okay. Thanks, Richard. Patricia, I'd like to get back to you. You're going to study a very interesting process, methane pyrolysis towards CNTs with 3 technologies. First of all, regarding what I mentioned before on the use of microwave technology and scalability, do you have an opinion about that, or you share the opinion of Marilena?
Yeah, I share for sure the opinion of Marilena, and indeed in storming we are considering the 3 technologies. because we don't know which one will be the most feasible for scaling up, because in our process we need to control a lot the reaction parameters, because if we want to grow the carbon nanotubes, it will be very important to keep the temperature. And because as we are generating the carbon, we are changing the heating way. So we are changing the resistivity, we are changing the dielectric properties and the ferromagnetic materials. So this is something that I try to tell you. This is a complex system. So before we are currently moving from TRL3 to TRL4, and we are analyzing the effect of these parameters in the process. For sure, using these electrified reactors, we have the advantage that you can change the power, you can change the resistivity fastly than with another type of reactors. But for the scaling up, this will be a problem because we are generating a solid.
But based on literature and prior work you've done in the field, do you have an idea already of how these three technologies compare in terms of efficiency, in terms of temperature gradients, attainable temperature, scalability? Any light you can give us?
Okay, for sure. As it was said also in the presentation of Total, the easiest one to be scaled up is the Joule heating, because we have more control temperature. As you were saying before, we were considering also the gradients of during our structural catalyst, and we are trying to overcome them with the electrical contacts and so on. But for sure, if I have to do an scale right now, it could set Joule, then followed by induction and then microwaves. This maybe could be a scale of scalability.
Okay. You also mentioned in your presentation that actually the final goal is to produce CNTs with high quality. Can you elaborate a bit on that? What kind of quality do you mean? How do you see metal contamination of CNTs? What kind of purity would be required to use CNTs in batteries? Can you comment on these things?
Yeah, the goal of storming is to produce CNT without iron, because of we want to regenerate the catalyst. So if we want to regenerate the catalyst, we cannot lose iron also within the carbon nanotubes, because if you have carbon nanotubes with iron, you are decreasing the properties for the batteries. You should treat them again with some acid, and you are detaching your active phase. So our aim is to control the catalyst and the reaction condition, always having a high productivity, because chemical vapor deposition is already done for doing carbon nanotubes, but they are not considering hydrogen, so only carbon nanotubes. So we want to combine the hydrogen productivity with the carbon nanotubes productivity. So the iron content is one parameter. Then we are checking the number of walls. We are we can prepare different nanotubes, and the site principally of the diameter. We will do also tests within a storming of the performance in the batteries. So we have in the consortium a partner that will check the performance of these carbon nanotubes in batteries.
But in principle, the goal is to produce pure nanotube, pure CNTs without any iron there. Okay.
Yeah.
And how are you going to remove the CNT layers from the catalyst?
Okay, with what we are calling these chemical scissor treatments, and because also in the literature you can remove then inverse in the reaction, because you can cut them with some reagent just at the base, and for instance also in the fluidized bed they are already detached during time on stream, because when you start running the reaction, then the adherence to the catalyst is not so high that you can detach them. So we can combine either a chemical process, so just remove the linkage between the metal and the carbon nanotubes, or also doing it mechanically.
You'll try both in the project.
Yeah, we are trying the first one, but we will have to use probably both of them.
Okay. Can we move on to the efficiency matter that you mentioned? You mentioned some numbers, I think, in your last slide. You mentioned that the target is to reach 60% efficiency and 95% selectivity.
100% selectivity, because we are only producing hydrogen, because
Does this
we
mean
are
carbon selectivity, so no carbon black or soot, or just
this is in the gas phase, because we are keeping the temperature low enough to only produce hydrogen. The efficiency was considered. This calculation were done considering the methane cracking advantages and also our technology, and considering the energy to produce 1 mole of hydrogen, considering that we don't need to evaporate water, we are using renewable energy and other parameters. So this is the 60% value came from this.
Mm-hmm.
Can you hear me?
Yes, I can hear you. So I have in mind some patents on the process from Bayer 2000. It's an old process, huh? From 2009, and another one from 2016 in fluidized bed and fixed bed reactors, respectively. The 2009 one used ethylene as feed and a little bit of methane. So it's basically the outlet of the steam cracker. In 2016, what they presented, well, it's an easier process. They start from methane, they do the process in a fixed bed reactor. They report 40% conversion of methane and I think 90% selectivity to CNT. So 90% of the carbon produced is carbon nanotubes, is in carbon nanotubes. So compared to these values, how do your project stands in terms of goals? You talked about selectivity already. How about conversion?
Okay, our aim is we are thinking about hydrogen productivity. So our aim is to reach hydrogen productivity higher than 5-6 liters of hydrogen per gram of catalyst per hour. This will depend on the conversion, because this will depend on the feed that you are feeding to your reactor, no, in the gas hourly space velocity. So our aim is to reach these values of productivity. We can reach them with 70%, with 90% of conversion. It will depend on several aspects, because the carbon nanotube growth without iron particles, we have to perform it under very careful condition, because if not, your carbon nanotubes are contaminated.
Yeah, I'm asking because in the graph that you presented in your third slide, where you have conversion versus temperature at 850 degrees, you don't get more than 40% actually. It's a low temperature. You need it. Can you go? Maybe I'm wrong. Can you go to the slide?
I think that you reach a little bit higher, because we are.
Okay, maybe. Let's see. I want to understand, and maybe the audience, how further you can go with respect to state of the art.
This?
Yeah, so.
A moment.
So what is the target operating temperature, and
okay, and this is in Kelvin.
What would be the expected conversion? Yeah, can you, so what would be the temperature that you'll be working at?
Okay, we are working at temperatures below 800 degrees C. So this is in Kelvin, so we'll be more or less here.
Yeah.
So we can reach conversion up to 90%.
Up to 90%, okay.
Yeah. This graph I took from an article, because it can be said, because there are some claims that depending on the type of carbon nanotube that you will form, your conversion will change, because you are changing your product. Yeah. So for sure we can reach conversion above 80%.
And if I see the left graph, so multi-wall CNTs require temperatures of 700 to 800 degrees Celsius.
Yeah, we can produce them. We are producing them at 700 degrees C right now.
Okay. And can you please define again the 60% efficiency? What is the definition exactly?
This definition was considered, and I was waiting also to Haidir, but they cannot participate. We consider and taking into account the enthalpy of the reaction and the amount of heat that we have to provide in comparison with the steam methane reforming, and considering that we don't have to provide heat to evaporate the water, and considering that we have an electrified reactor where all of the energy will be transferred to the reaction. So we don't have heat to heat the gases, so we will use them. And we consider then the amount of energy produced for the hydrogen. So more or less, these are the calculation.
Thanks, Patricia. I have a last question related to fluidization. If I understand well, you're going to do fixed bed experiments and fluidized bed experiments, correct?
Yeah.
Okay. These two types of reactors, as you know, and most likely you're going to work in the fast or turbulent fluidization regime because you need to get the catalyst out. Yeah. So the residence times will be different in the two types of reactors. You'll have the same temperature, or at least you target the same temperature, the one that is needed to produce carbon nanotubes, but the contact times will be different.
Yeah, indeed, the conditions
don't expect different results. Why do you want to study both?
Yeah, for this reason we are studying both, because we know we have also different residence times, and so we will grow the carbon nanotubes in another way, but we have also another parameters that with in the fluidized bed we are detaching the carbon nanotubes, so we don't know when we will stop the growing. So as for us, it was important also to control the growth of the carbon nanotubes. For this reason, we also decided to go or to move to a fixed bed, because there the conditions are more controlled, because you will only detach the carbon nanotubes when you will apply the regeneration method. For sure, we are generating a high pressure drop, and that's the reason that we are using a structural catalyst, to have more room for the carbon nanotubes to grow. We know that it's more efficient to have, I think that Anton is there. We know that fluidized bed is more efficient. You can run the reactor for longer time, but maybe with paying a price in the quality of the carbon nanotubes, because you don't have so control condition. I think this. I think that Anton from Haidir is there. Okay, that because he's our partner from that will do the scale up, and he's telling that the hydrogen will be separated in a PSA, and it will be then circulated. And the off gas will be circulated.
Yeah. And I guess in order to design an optimized system, and again, I'm making this question, but because they're also relevant to the other projects, for example, to Titan, you really need to simulate, to model the process in order to design it properly. And these models are complex. You need to combine electromagnetics with flow, with heat and mass transfer, and with kinetics of these processes. Are they available for pyrolysis?
We are
both
doing
in gas
that.
phase and the growth kinetics of carbon nanotubes. Do you have this information, or are you going to do such studies before you get into modeling and optimization? Is that the idea?
In storming, we're doing kinetics studies.
Yeah.
And
yes.
in Titan we are using or doing all the modeling that you mentioned, electromagnetic kinetics and flow dynamics and etc. So, and we are doing that both in Warsaw and obviously EReTech and ourselves.
Okay. And the issue of carbon contamination is relevant to the Titan project. I think David mentioned that, because you want to use the carbon for soil improvement. How can you address this problem? How do you plan to address it? How can you, produce pure carbon, non-contaminated?
Our carbon is not, as long as we use a catalyst Okay,
Yeah.
our carbon is not going to be pure. Our carbon is going to contain the catalyst inside. This is why we are looking at different catalysts and what is allowed for the agriculture. For example, iron, carbon and iron. That shouldn't be a problem, but the University of Hohenheim in Germany is our partner, and they are looking already into what's happening when we apply this carbon as a soil amendment. So they are looking at life of organisms, I would say, in the soil. They are looking at color of the soil, and there are some other analyses that I can't remember in terms of that. We are also looking at using this carbon in the industry, those industries that do not mind the catalyst in there. So we are also looking in parallel at other applications. But we are not going to separate the catalyst.
Okay, sounds good. Biogas contains some impurities as well. Sulfur, nitrogen impurities.
Exactly, and we are going to also,
yeah,
we are going to look into that as well. So for the time being, we make the biogas ourselves, so that there is not such source of biogas next to us. So we are making methane CO2. It's easy to, from bottles, and we'll be adding H2S. We will be adding this kind of sulfur compounds and probably some other stuff that the European Biogas Association are there, and they are going also to support in choosing the right recipe to test. So we are going to add them both for the lab scale and the scale up to the TRL 5 to 6.
Yeah, I'm mentioning that because in reality, the actual electrified plants might be, more complex than what is presented, and this affects the economics and
for sure, like
their economic viability. Yeah,
for sure.
Yeah. Okay, thanks. I'd like to move to the SiPox technologies. This is Gianluca.
Yeah, I'm here.
Hi, Gianluca. Can you hear me?
Yeah, I can hear you.
Yeah. I think, you have the advantage of working with a technology that I feel it's at a higher TRL at the moment, more scalable at least, correct? But looking at your presentation, I have some questions that I'd like to discuss with you. So you're placing the heating element inside the tube, correct? And this occupies a fraction of the volume of the tube, correct?
Yeah.
How much this fraction is? Can you comment on that?
Well, it's a considerable fraction. I cannot tell you how much is the fraction because that is affecting a lot heat and mass transfer and all the stuff. But yeah, it is a considerable amount of the.
Is it something that is optimized in the design?
Yeah, it's something that we have been optimizing in the design.
Yeah. And is there a risk of that being coked? So, is that coke deposition on the heating element that hampers heat transfer over long times or not? And does it also generate the risk of clogging of the reactor?
Yeah, well, let's say during all the operating hour we have been doing reforming, we never had a problem on carbon formation as long as we were having steam entering into the reactor. And actually there was something very interesting that is you can operate also a very steam to carbon ratio also when you are co-feeding CO2. Well, and we have not deeply investigated this, what is the reason, but one of the reason we are giving is that if you cut the reactor, if you do a cross section, well, the thermal gradients that you are having there is very low. So the heating element is very close to where the catalyst is, and the gap that you are having of gas is also very small. So this is kind of homogenizing the temperature on the cross section, and this is yeah, you are having a certain temperature profile that is helping on minimizing the possibility of carbon forming potential.
Mm-hmm. You also mentioned it is the case that you use less catalyst compared to a conventional reformer using based on the geometry that you're using. Does this imply that you also need to use more active catalysts, using, you know, employing precious metals, more expensive ones?
Well, maybe not. Okay, in the meaning in a traditional reformer, you are having much more nickel than actually you are using, but you are simply putting it, but you are not able to use it because of mainly temperature profile reason, right? So one of the things that needs to be addressed is in an electrically heated reactor, I can achieve intensification, meaning I can have a reactor that is much smaller. This would lead to the possibility to allocate much less catalyst compared to a normal reactor. And then the question is, well, then is it the testing procedure that has been used until now for a lifetime assessment and qualification of a reforming catalyst can also be translated to a nickel catalyst that needs to go into a reforming, into an electrically heated reactor. So in principle, the activity, for instance, of the nickel is very high, but well, what we need to do is ensuring that that the few amount of nickel that we can put in is not deactivated, is not whatever poisoning, sintering, or whatever is doing.
Considering the reactor geometry that you have a tube and the heating element at the center. So you have an external wall, an internal wall, which is the heating element, and the gas that flows in between, right?
Yeah, correct.
Correct. Conceptually, what is the advantage of this design with respect to design that you hit not the internal wall, which is the heating element, but the external wall, where the catalyst is coated?
Well, you need to, how would you like to heat the external wall? Sorry?
With resistances, with radiation, with microwave radiation, with whatever. I'll leave the combustion aside, what happens outside the tube. I'm focusing on intensification of heat transfer inside the reactor. So from the wall to the gas.
Yeah.
Okay. In one case, in the technology, in the configuration that you presented, you hit the internal wall, the heating element inside the reactor provides the heat. In the other case, it's the coated wall that is heated somehow. It doesn't matter how. But in terms of heat transfer from whatever wall to the gas, does this make any difference? Is there a conceptual advantage? This is what I'm trying to understand. The superiority of your design with respect to heat transfer to the gas as such.
Well, this is the gas is in direct contact with the heating element. And well, let's say this is kind of, well, you see like the heating element in the pipe, but well, that heating element is for sure also heating the ceramic material, right? And for the ceramic material that is on the next is not inside, is outside, right? So at the end, the important thing is which surface to volume ratio you can have inside the reactor. Okay, because you will be limited by a certain heat flux at the or a surface load of the heating element, and you need to allocate a minimum amount of surface inside a certain reactor. Okay, and the difference on having the heating element inside a ceramic microstructure is that you are maintaining decoupled the catalyst and the heating element. And it's not that the catalyst is playing both roles, right? Because if you could have an electrically conductive catalyst carrier, you could use the carrier as an heating element, right? But you understand that, well, the carrier needs to play two roles, that is heating element roles and carrying also the catalyst, And well, this is the question is, do you really need to have that, or do you simply need to have the heating element close enough to the catalyst?
Mm-hmm. Yeah, and maybe my final question related to what I asked just now. Do you have values or ways to define energy efficiency for this reactor, and do we know how it compares with conventional steam reformers in terms of energy utilization efficiency?
Yeah, well, we are having, I mean, if what can be simply done is you know how much electricity you are providing to the heating element that is within the reactor, and then you do an energy balance, whatever. If you are on a simple heat transfer, you know the flow rate, you know T in, T out, or if you're doing a reaction, you know conversion T in, T out, and then you can quantify the duty that you would have needed. And of course, this depends a lot on the scale. In the meaning, if you are at a very small scale, the heat dissipation that you are having on the cable that provide the electricity to the heating element, or the loss of heat that you are having on the penetration of the electricity into the pressure vessel, is becoming significant compared to the power, to the energy that is actually going into the reaction. But well, we have shown that we can achieve 95% efficiency, so electricity entering into the reactor, and this transfer into the medium that needs to be heated or converted can be as high as 95%.
Yeah, so this is a ratio, yeah.
And of course, let's say you were asking what is normally the efficiency in a firebox, right? So, well, you are having a burner that is burning 2 and is transferring more or less 1. So you are at 50% efficiency there. And that's the reason why you need to claim all the heat in the convector.
Yeah, it's less than 50%. It's 40 to 45, I would say. But still, overall, the furnace is a very well thermal integrated system with efficiencies in the order of 95% overall. That's why I was trying to compare this with the efficiency of your reactor. But you're telling me that the electricity, the fraction of electricity that goes to the reaction, to chemical energy and sensible heat, so temperature of the product, is 95%.
Yeah, we have shown that value with the experimental data.
Okay. Okay, thanks a lot, Gianluca. In view of the time, I'd like to move on with the last presentation, the e-CODUCT project. Gleb.
Yes.
Well, thanks a lot for your presentation. It was I had never seen this technology, so I learned a lot myself about it. Can you, maybe that's useful for the audience as well, can you comment a little bit on the dimensions? You haven't mentioned the diameter of the system. That's one thing. And how tall can the reactor in principle be? What is the...
because we
it's
work
3 meters now, understand, but yeah.
Yeah, it's total dimension, because we work in quite an extreme conditions. Also, it's 1200 degrees, and also selection of materials is rather special because we have carbon monoxide, we have sulfur vapor. So the internals, the inner diameter is something like 12 or 14 centimeters. I can't recall the exact number, but we aim on standard materials available on the market. So it's one of the standard DIN dimensions. And the active zone will be roughly half a meter, including this upper electrode connection, and the rest is basically insulation and connections for the thermocouples.
You mentioned that this technology enables uniform heating of the catalyst. Is that correct? Did I understand well?
Yeah, basically the goal for fluidization here, because we have in simple words, some kind of hot core where the heat is created. Without fluidization, we will have a gradient, so it's unavoidable, thanks to not only short residence time, but also good temperature distribution.
Do you measure that, or do you have such, have you quantified these gradients via modeling or something? Do you have any data?
There are simulations which are done
On the
actually
radial
by
temperature gradients, yes.
yeah. We expect almost no gradient across the bed. Of course, once we reach this walls, we want the contrary. We want as high drop as possible, because the reactor will be installed in ATEX zone, and we need to respect ATEX conditions. So the outer wall should be cold.
And yeah, since if I understand well, then it's not the electrified technology, but rather the fluidization regime. You're working in the bubbling fluidization regime, I guess.
Yeah.
That creates the uniformity. Then, similar to the question to Gianluca, what's the conceptual advantage of this design compared to a conventional fluidized bed reactor?
So the way we provide heat in conventional fluidized bed is basically the catalyst is the heat carrier after regenerator, because we burn coke which formed on it, and we transfer it back. Here it's endothermic reaction, and normally we don't deposit anything on the catalyst. So in principle, the same approach we can't apply. One option would be is to have hot wall, so we some kind of fire heater for the wall of reactor, but then we need to go for very thin tubes and have some kind of multi-tubular system to ensure we supply enough heat to make the reaction happen. So the main advantage is this cold wall concept. Yeah, when we generate it inside, in principle, we are close to 100% efficiency.
Yes, 100% efficiency of the current to heat inside the reactor.
Exactly.
Okay. Do you have any energy losses in the hardware itself, in the power generator, in the electrodes? Any?
Yes. So it's pretty close to what Walter presented. So we go down to maybe 90%. It's just heat formed somewhere else and some losses due to electronics operation, which are unavoidable. But this is the limit of any electrified approaches.
Yeah. And you mentioned as an advantage that you can higher flow. You can apply higher flow rates.
Yeah. So
process more gas with this technology or not? This is what I had in your slide.
So
short
here,
residence times, high speed. Yeah.
In principle, this carbonyl sulfide, it's a metastable molecule. So if we leave it at low temperature, then it will gradually disproportionate in carbon disulfide and CO2. And so we work in kinetically controlled regime. So we want to have more cracking happening than disproportionation. And with short residence time, we are able to achieve this.
Yeah. So you're able to apply higher flow rates compared to a wall-heated reactor, for example.
Exactly.
Is that the? Yeah. And have these metrics been quantified? How much you can increase the throughput with this reactor compared to a benchmark? I'm trying to set up a benchmark in my mind, a benchmark technology, so I can compare the performance in all relevant terms.
No, this is in progress. We need to see what are the limits. The reactor here was specifically designed to accept 2 kilograms of feed per hour. How much higher we can go related to this design, this I can't respond.
Okay, thanks a lot. I hope we generate some more information for the audience, but I feel we all learned more about these technologies, and that was the goal. Thanks, Joris. Words back to you.
Yep. Thank you, George, for chairing this round table discussion and having some remarks and questions to all of the presenters. If I look into the Q&A, I see that, well, as such, quite some aspects have been covered already, although one particular one was related to the potential impact of corrosion. And it was asked with respect to a few of the projects. Looking at it, so for example, but particularly for the SiPox technology, it has been requested. But I was also wondering myself within e-CODUCT, for example, because there we're having some particular molecules. So to what extent has potential corrosion already been an issue that has been observed and that has been thought of?
Yeah, absolutely. So, well, for the atmosphere that we are having in reforming, we did not have a problem on potential metal dusting or stuff like this, and mainly is because the heating element is actually able to withstand very high temperature, because the heating element is forming a surface layer of a compact material that is afterward preventing the further oxidation, or anyway the potential also diffusion of carbon going into the heating element itself. And well, this is a properties of the material that that we are using, but that is normally used in an heating element where you are mainly having nickel chromium heating element or iron chromium alumina material. Yeah, actually, we also with we are having a paper where we are a bit talking on this, why ferroalloy metal is able to withstand very high temperature. Also, Patricia is co-authoring that. I think that would be helpful to understand how come that this metal can have this performance at very high temperature.
Yeah. Okay, thanks. Another question, and maybe one of the other, well, technologies which has not come up, maybe because it's only partly related, but still is plasma technology. And the question was made in the context of the Titan project, what the quality of the carbon produced would be when compared with using plasma techniques to do the same kind of reaction. I don't know, Marilena, could you comment on that?
Yes, I in terms of plasma technology, there are processes related to striking a microwave plasma straight into methane, with no addition of catalyst. And there are also technologies that imply plasma and catalysts. So in terms of, if I refer to the process without the catalyst, obviously after the process you have methane decomposed in carbon, black carbon and hydrogen, while in terms of the catalyst, then that might be also involving the catalyst.
Yeah. Okay.
So in terms of the quality of the carbon, for sure it depends how you do your plasmolysis reaction. Do you do it without the catalyst or you do it with a catalyst?
Yeah, indeed, I see. I hope this also addresses the question that has been asked. Another question was going, but I see it has been answered to some extent already on the ēQATOR technology. To what extent it could be retrofitted in existing assets? I don't know, Richard, whether you would like to add something more there to the answer you had given. Oh, you're still muted, Richard. First time it happened in about 3 hours of workshop, so that's quite a success.
My mouth was moving, but no sound was coming out. No, there was with the electrically conductive honeycombs, we are wash coating our catalysts on them. in principle, you could wash coat any other catalyst to do any other chemistry. So it's just a question of the catalyst, whether it withstands the conditions, and how easy it would be to wash coat it onto these honeycombs.
Okay, yeah. Okay, well, and maybe then getting back to Titan and and again related to plasma or compared to plasma, was the question how the capex of a catalytic fluidized bed reactor would compare to a plasma reactor for methane pyrolysis. Could you comment on that?
Yes, I could. In terms of the microwave gear, but it's the same gear. There is absolutely no difference between a catalytic reaction and a plasma reaction, for example. So there are the same generators, same elements. In terms of the reactor itself, probably for the fluidized bed catalytic reactor, there will be all the costs related to fluidizing the bed and recovering the catalyst and recirculating it. So that is in addition to the a plasma reactor without catalysis. Okay, so I'm really comparing these two technologies. So the microwave gear, it's exactly the same.
Yeah. Okay. Well, one of the most recent questions was a very practical one related to EReTech. What is the inlet flow rate of the Pilot 1 project for EReTech, Gianluca?
The inlet flow rate of the pilot, 100 normal cubic meter per hour.
Okay.
Of biogas.
Yes. Yeah. Definitely. Okay. I think most other questions or comments which I had noted, I think have essentially been dealt with. So unless and well, also our time is more or less running. So unless there would be some very urgent question which one could type in the chat. I think the time has come to more or less round up our joint workshop. I think we had a very nice overview of existing and well technologies that are being developed in order to address the challenge of electrifying technology, electrify chemical processing. And well, as it seemed, maybe the most conventional way of getting electricity to practical energy by heating via the Joule effect seemed to be the most well robust or the ones where there was more certainty about it, but maybe not necessarily well, not inhibiting innovation in other technologies. Such as microwave and other manners of heating. And I think apart from the electricity, a lot went also into decarbonization, especially in the last two projects having to do with methane pyrolysis for hydrogen production. With indeed ways to effectively become carbon negative if you manage to do something useful with the carbon, if that is coming from biogas. So I think that are all very promising perspectives. So I think this is essentially what I wanted to to say as wrap up. Well, I see Marilena, you still would like to make a remark?
I raised my hand because I haven't seen any other questions. So I just take 1 minute to say that in terms of all this project, I see there are projects that would like to compare different electrified technologies for their reactions, including microwaves, and I'm actually a microwave person. Okay, microwaves, it's all electric, we know that, but I believe in terms that there was a question related to the uniformity of microwaves, and the uniformity of heating with microwaves is related to how we apply them, so we need to be very careful in that. And I also believe that in terms of, you know, us all succeeding in these technologies is to also think about combining different heatings, microwave included. So you know, when you compare induction heating, resistive heating, microwave heating, perhaps, you know, at some point that there will be also, it will make sense perhaps to think about how to use them together, you know. Hybrid heating is something that I believe in. There are industrial processes out there using microwaves and other type of heating, and they are very successful. And these processes, you know, they have probably they make more industrial sense in a way than just applying one technology or the other. Thank you.
Yeah. Okay. Thank you very much for this comment, and I think it's a nice conclusion also of the workshop. Investigating well, specific heating technologies can definitely be good to better understand them, but in the ultimate application, being able to combine them and establish synergies will certainly be recommendable and might be the topic of future calls for the European Union projects. So with this, I would like to thank all the speakers once more, also George for moderating the roundtable discussion, and of course all of you who participated, who attended, who asked some questions. I think it also contributed to the success of our event. Stay tuned for each of the projects and for a potential follow-up which will be organized in the future. So thanks again, and see you later.